All right. So before I actually go to this slide, I want to remind you what we did last time. So what is the law of large numbers say? Think casino. Yeah. Yeah, that's it. If you forget things casino, right? More people gambling, they guarantee return. So that means your X bar is get closer and closer to your mu, which is what we want to estimate. And another thing is the central limit theorem. Central limit theorem. Yeah, have we finished that? Sort of. At least we kind of go through it. Okay, what central limit theorem say? As n get larger and larger, right? Large at least 25, then the sample mean distribution. This x bar means sample mean distribution. By the way, the small x bar is sample mean. The big x bar is the sample mean distribution. I mean a lot of little means, right? A lot of little sample means. A sample mean distribution is approximately, somehow I use the notation little squiggly thing, normal with the same mu. And the standard deviation is sigma divided by square root of n. Notice that mu does not depend on n. Now, this is a very powerful theorem. If my population is normal, then I'm okay, right? I can write out of the problem. I can say x bar is approximately normal. This. What if my population, my parent population is not normal? Then what condition do I need to use CLT? What if the population is not normal? Then what do we need? What is the backup that we can use CLT? You need what? Your sample has to be at least 25, right? At least 25. If it's below 25, nothing you can do. Maybe you can try to graph it to see if it's normal. If it's normal, then great. We should proceed with this. If not, nothing you can do. Right? Okay, so remember this formula is in your stat card as well. All right, so let's do this one. Suppose the random variable x represents the actual flight time in minutes for Delta Airline flight from Cincinnati to Tampa. Follow a uniform distribution. So this is your. Yes, go ahead. Say it again. Instead of.
Like say above 134, why don't you use 135?
Above 134, it could be 135, 134.1, 134.2. Now this is continuous random variable, it's not discrete. That means you have to count in between 134 and 135 as well. When it's continuous, use if you can use normal distribution, use it. It's continuous random variable because our problem is what our problem is say what is right here. X represent overall score of 20 years old. Such score are normally distributed. What you said is you try to use binomial distribution. Remember, binomial is a discrete random variable, right? We only care about the count. We don't care about what's between the numbers. But when the sample size get large, let's get what hairy, right? Get a little cubism to calculate. So if the sample size get large, and you guys remember the condition when you allow jump from binomial to approximately normal, what is the condition? No.
Greater than
10, right? N times p is greater equal to 10, and N times 1 minus p greater than 10. So that's nice things about a normal distribution is kind of let you use the formula instead of doing little count. For this problem is already normal, so let's just use that. But you are you okay with the procedure? Okay. I know that I don't show all the math. I kind of use R. But this is just review. You guys did this in exam 1. All right, now the flight times. So the parent distribution is uniform. It's not normal. Uniform. Uniform. It look like a box, right? Can someone tell me what's the distribution? Oops, sorry. Can someone tell me what it's the distribution of this uniform? The notation for the distribution. UAB, right? UAB. And what is A? What is B? Yeah, so from 110 to 130. Okay. So just plug it in, 110, 130. And probability distribution function, PDF. That's your height. It'll be what? 1 over, yeah, B minus A, right? The 1 over 130 minus 110, which is 1 over.
You guys are good.
All right. Okay. Now the problem doesn't ask you about the mean, but I need the mean. Because later on I need it. I didn't give you the sigma, didn't I? I forgot. I'll look it up what the sigma is, but I should have give you the sigma in the problem. All right. Can someone tell me what the expected mean here for the time for the flight times? Remember this E of X. Exam 1. I asked you time or plus? Average of A, B, right? Remember, average mean in the middle, right? So just add them up, divided by 2. 110 plus 130 divided by 2. What is it? 240 over 2, 24 divided by 2 is 12, 112 minutes. That's E of X. Can you recall? Do you guys recall about exam 1? Okay. I need to give you the sigma. I need to give you the sigma. I forgot where it is. Never look it up. Chapter 15. That's a formula for sigma. I forgot to, but I'll give it to you. You don't need to calculate it. Sigma is 5.8. I'll put right here. Minutes. That's my standard deviation. I got mu, right? E of X. I got mu. I got sigma. Right, that's my parent population. Now, suppose we take a random sample of 100 such flights. Now we talk about sample now. Record the 100 actual flight times and compute the sample mean for these 100 actual flight times. We will have our first sample mean value. Consider repeating the process over and over for a total of 50 times. So you pick another 100. You pick another 100, 50 times, resulting in 50 possible value of sample mean. And then what you're gonna do with those sample means, you're gonna plot it, and then you get a histogram of 50 sample means values. They ask you to provide a smooth out sketch, density curve. Okay. It's histogram, so it's gonna be have that normal look. Everybody can do this. It look like this. Okay. I'll try my best. It's just difficult to make it symmetric. By the way, it's very rare in practical life you have a symmetric data. Rare, right? Usually it's skewed a little bit to left, skewed to right. We don't have a perfect word. All right, so Now, these the distribution of a bunch of X bar. Can you tell me what is the distribution of sample mean? Remember the big X bar. What's the sample size here? 100 is a big, it's bigger than 25, right? It's definitely greater than 25. Greater or equal to, oh, I'm sorry, 100, no, 10. So, according to central limit theorem, X bar approximately, yeah, so X, okay, I can't, mu comma sigma divided by square root of n, which is, I can't write the end. What's mu? We just calculated it, 120, right? Sigma is 5.8. I provided to you. 5.8 divided by square root of 100. What you guys have? 5.8 divided by 10. Square root of 100 is 10. Oh, I gotta run. So mean, just divide. 0.58. I don't know why I'm gonna use a calculator. Okay. Let's just move one over. I guess I just want to try the part. Okay. All right, that's all they want. I think that's all they want. Draw. Oh, you're gonna no, you're gonna label it too. So 120 is right here. And what is my X label? X is, what's X represent? Sample mean flight times, right? Average flight times in minute. And the Y just the probability distribution. So it's just frequency, but we don't usually say that. Now, question for you. There's no computation here, just critical question. Suppose instead of taking 50 random samples of size 100, we took 200 random samples of the same size, still 100, just instead of 50 times, we do it 200 times now. Will the distribution of the sample mean change or stay the same? There's no calculation here, just critical thinking. If I'm doing it 200 times instead of 50 times, would my mean change or stay the same? Thank you, Jade. Stay the same. Why stay the same? It's correct answer. Why stay the same? Okay, okay. It doesn't change. It's just the only thing changing. You just repeat it more rather than you did. But I want more concrete answer. You're almost there.
You'll have like a smoother bell curve, but it won't change what that bell curve will be.
Good, because according to the distribution,
We don't, there's nothing that
yeah,
comes out.
mu does not depend on sample size, right? Let it stay all by itself all along. Right, so whoever chain is stay the same, right? Because mu is done. Because from the distribution of X bar, which is approximately normal, mu sigma divided by square of n. This imply mu does not depend on n or number of times of repetition. Repetition. Okay. All right, second one, you should be able to answer again. Instead of taking 50 random sample of size 100, I'm gonna take 50 random sample of size 200. What that means, sample means that the same or change. Stay the same, right? It does not depend on n, right? Stay the same. Yeah, distribution of the sample mean change will stay the same. Maybe I should answer two part. So part is mu and the standard deviation, right? Maybe here I'll answer two part. So bullet point and then another bullet point. Maybe I'll use blue. So this is the mu part and the standard deviation part. In blue. I should write it in blue. So I guess I'm not finished with that this one. I was gonna do it second one. I guess I can do both. What about standard deviation for the first part? Is it change or stay the same? Is your sample size still 100? It changed, yeah, it changed. Oh no, it doesn't change because the sample size stays the same, right? It's still 100. Still 100. Even though you repeat many times, but your sample size is the same. So nope, doesn't change. Does not change because sample size n is still 100. For the second one, mu still the same. No. Same reason above. What about standard deviation? Change or stay the same? Change. Smaller or bigger? Smaller, right? Anyone see that? Get smaller? It's simple math here, right? Instead of 100, you put 200 in the bottom. So denominator is big, mean fraction small, right? This is a good quiz question. I'm gonna have something like this on the quiz. I'm gonna give you something and then I'll ask you about the standard deviation in a minute.
So whatever the distribution of the original population is, if we get a distribution of mean, will always be normal.
If it the sample size is greater or equal to 25. Yeah. Now sometimes it's below 25 and it's still normal. We get lucky, but that's you have to check. You have to graph it. Here I cannot graph it because I don't have data points, right? For the problem that you don't have data points, I have to tell you first, right? I have to tell you if a parent population is normal, then you're okay, right? It's kind of safe to kind of roll the ball, with the normal distribution for everybody. But the parent population is not normal, then you have to take a look at the sample size. If it's less than 25, you cannot do anything. You just kind of stop. I don't have enough information to proceed. But sometimes if it's less than 25 and you have data points, then you can graph it and you can see. We'll get into that example as well. All right, so here just a reminder, sampling distribution. So far we learned about sampling distribution of X bar. So small. So I got X bar, what else? What other statistic that we know? What other statistic? Huh? Variance, good. And standard deviation, right? So far, 3 of them, right? But we only focus on the X bar so far. We kind of studied that's X bar. I'll now tell you why right now. Now, every statistic has sampling distribution. Why? Because if you repeat it many times, you're gonna produce a bunch of X bar, you're gonna produce a bunch of standard deviation, you're gonna produce a bunch of variance, right? And you plot it on the x-axis, you're gonna have a somewhat a curve, right? Is it normal? I don't know. Well, X gonna guarantee normal if you can increase your sample size. But let's take a look at variance and standard deviation. So here is, do you guys remember the Y tasting data, the DMS order thresholds? Now they take 1,000 simple random sample of size 5 from a normal distribution. Now, if it normal, then I'm pretty sure my X bar is also normal. Let me include one more thing here, the median as well, sample median. Should I say sample median? You can have a bunch of sample medians. So for the first picture, what they do is from the population, they took a simple random sample of size 5, and then they compute the first median and second time, same size. You got the second value of median, and then they do the same process for 1,000 times. For 1,000 times. So simple random sample, same size, and this is M of 1,000, right? And then they plot it on the x-axis. They plot it on, and this is what they see. They see a normal distribution of all medians sample from the sample of the same size 5, right? Is it always like this? I don't know. I cannot tell you. I don't study about the sampling distribution of median. Usually we only focus on the X bar. Maybe we got lucky. It turned out to be low. So many 1,000 data points, right? But I don't know. I can't tell. I never guarantee it's always normal if you increase your number of repetition. For sample variance, they do the same, right? They have 1,000 variances. They compute it, and what shape is this? Right skew, right? If it right skew is no help, right? It's not helpful. It's not. I don't have a formula for right skew, so this is not very helpful. This is standard deviation. It's a little bit better, but it's still what? It's still right skew. So right skew, left skew. Yeah, I got messed up with the tail now. It's the right skew. I got messed up with the goodness. All of a sudden I forgot. I got messed up with the skinny part, the big part. Should be here. Can't believe I forgot. Right here, right skew. So that was the right skew. Left skew, the skinny tail. Okay, all right. Left skew. That's it. That's it. That's why we study sampling distribution of the X bar, right? Because of CLT. And that will be conclude our chapter 15. So